No worries. Yeah, so this is a talk like I put together from the work using extreme events. And with extreme events, so extreme values, as you probably know, they are usually in the tails of the distribution function. So these are rare events, rare values, and then the related events we call extreme events, right? So in terms of weather and climate, you can think of heat waves, cold spells, maybe even tropical, not even, but also tropical cyclones. But so from this perspective, an extreme event is a rare event, so it's always surprising in a way, right? But I would argue here also that there are several degrees of surprises. So some extreme events are more surprising than others. And there are, of course, different reasons for that. So for example, what can cause a surprise if we are talking about a rare or extreme event? You might have the situation that you basically don't have enough information. So if this is some temperature time series over like almost or more than 70 years, and you see that there is one event here towards the end, which is much more extreme than everything else you can see. But this might be also only because you don't have enough data, right? So because of the short length of the data set. And then there are, of course, certain variables also in the climate system which often have so-called fat tails. So a fat tail is represented by the red line. We are looking at probability densities here, and you see that the probability density in case of the red line decays slower than in case of the black line, which is exponential. So sometimes you get these properties of the tails or probability densities that generate you more surprises or more extremes. And then there are also the non-stationarities which can lead to extremes, right? And we can think here of global warming, but also like if there is a tipping point that might lead to surprises as well. And actually in case of this time series I showed you, this was, it relates to the location shown, to that region shown on the right, on the left. And so this extreme value is due to the 2021 Western North American heat wave, which is was one of the, was a record-breaking event at that time. So in this case, then also global warming, also the non-stationarity has a role in making the event surprising and making it extreme. And then, of course, surprises are also always a matter of perception. So there is a human perception bias. And for example, Iris de Vries showed in case of rainfall extremes that regions without record-breaking events in recent history are more likely to be less prepared to extremes. So in this talk, I will not go into the perception bias. So it's more about the physical properties or the properties of the system that lead to surprises. And there are three main parts of my talk. So first, a bit of theoretical ingredients for you to understand then the results later on. Then I will show you that extreme events related to large-scale atmospheric anomalies are relatively unsurprising. And then at the end, I will discuss, okay, but so when and where do we find surprises? So where are surprises coming from? Okay, so let's start with a bit of theoretical ingredients. And a very commonly used tool to analyze extremes, statistical tool is extreme value theory. And one of the extreme value theory methods which is widely used is the peak over threshold method. So I will just explain you shortly what is it about. So we have some independent identically distributed random variables, and we select exceedances over a certain threshold, as you can see, for example, on this figure here. And we are looking at the probabilities of these threshold exceedances of the values above a threshold. And then it has been shown that if this threshold is large enough and under certain conditions, the distribution of the threshold exceedances converges to the generalized Pareto distribution family, the GPD, which you can see there. And then there is like a similar law for block maxima and another distribution, but the same idea, basically. And this generalized Pareto distribution contains actually 3 different types of distributions with 3 different tail behaviors as shown by the shape parameter, the xi. So if the shape parameter is negative, then the extremes have an upper limit. You can see it here on the blue line. So no larger extremes than those extremes can happen. And in that case, basically, if you already experience everything that is there, you cannot have surprises. Then in case of a zero shape parameter, the decay is exponential. So theoretically, very large extremes are probable. So surprises are probable, but their probability is very low. So one doesn't have to worry much, maybe, about surprises. But then we have the case when there is a fat tail, like the red line, as I mentioned before. In this case, the tail probability decays polynomially, decays slowly, so surprises are very probable. Now, if we want to express this in the terminology of swans, like I was recently reading this book, which is a great book, and I think if one is interested in extremes, is really nice to read. So the fat tail probabilities are the ones who produce gray swans. And then the first 2 are more like, extremes are more like big white swans. But yeah, so not very unusual, not very surprising. So then you might wonder, okay, so where are the black swans, right? And then also nowadays, every time an unprecedented event happens related to the climate, we hear very fast, okay, a black swan event, was it a black swan event? But actually, black swan events occur in systems which are not, in which extreme value theory generally is not applicable. So sorry to disappoint you from that perspective, so I will not talk about black swans here. But yeah, a bit about these big white swans and or more about the big white swans and a bit about the gray ones. Yes, another tool which we can use to study extreme events, and in this case we focus more on the persistent extreme events, like you can think of a heat wave which lasts several days, or a cold spell as well, can last even 1 to 2 weeks, right? And a useful tool to study them, these persistent events, is large deviation theory. We have again some random variables, and then in this case we average over finite length blocks. So we look at these finite size averages, and under certain conditions we obtain a large deviation principle for large block sizes, after which then the probability of averages decays exponentially if we further increase the block size, as it is expressed by that equation there. And that function I of a is very important. It is the so-called rate function. It describes the speed of decay of probabilities as we average over longer and longer block sizes. And you can see here an example for a rate function. The red line is a rate function in case of Gaussian random variables. And you see that the rate function is positive almost everywhere, and it's larger at the tails, because then the probability of averages decays faster as an effect of averaging, and it is 0 at the mean of the distribution, which corresponds to the law of large numbers. So if you plug in 0 there, then you would get the probability of 1. So large deviation theory is related to the central limit theorem, but it is an extension of the central limit theorem. It gives us more information. And the rate functions you get, they depend on your original distribution of the data you start averaging. And for example, the rate function is quadratic in case of Gaussian random variables, and it's not quadratic in case of exponential random variables, but it's always quadratic close to the mean because of the central limit theorem. However, the large deviations can be different from the small deviations, and that's why it can have a different shape when we go towards the tails. And there is something special about quadratic rate functions, which I will try to explain to you now. So for example, let's take the exponential rate function. So on the right, for the right tail, this rate function is asymptotically linear. So it is almost linear if we go towards the tails, and that means that if we consider two anomalies with a certain distance, and then we increase the anomalies, but we always take the same distance, the difference between the probabilities will not change. So it means that not much happens if we go more towards the tails. But something happens when we go towards the tails in case of quadratic rate functions. And that means that what happens is that the difference between the probabilities of two equidistant values is increasing. So the more you go towards the tails, the more extreme values will dominate your averages, and then the more similar your average values are, or the more representative they are. Because of this quadratic shape, or also if you have a rate function which then increases faster than quadratically, you would have the same effect. So if the large deviation principle applies generally, it means that large values don't dominate the mean. So your mean is representative also in case of the exponential rate function. But then when you go towards the tails, only in case of the quadratic rate function, you have this effect that the more extreme the events, the more similar they are. And large deviation theory generally describes the most likely of all the unlikely events. So it doesn't describe like super surprising events. And now a bit about the large-scale atmospheric circulation anomalies and their way of producing extreme events. So here you can see like a short movie for geopotential height anomalies. So these are basically pressure anomalies. And in the middle, you see the North Poles, and you see our hemisphere. And what you see is basically the propagation of Rossby waves, of the anomalies related to Rossby waves. And so you see a lot of structures, right? Structures as anomalies, and they can create extreme events. But then the large-scale circulation produces extreme events not by producing like new structures, which you don't observe here, but it's producing extreme events more by making the structures you see persistent. So by decoupling them from the rest of the circulation, or like blocking maybe almost the whole circulation and making this structure persistent. And we are interested at these persistent events, large-scale circulation-related persistent events, not because of their, let's say, the intensity or also their duration, which have a big effect as well, but also because these events are also usually always big, because they are related to large-scale anomalies. So for example, that was a recent cold spell in 2022 in the US, and you see that almost the whole continent is affected by the cold values. So they are big, and the Rossby wave dynamics tends to generate also co-occurring extremes. So you can have, for example, several heat waves hitting different locations on the hemisphere almost at the same time. And especially if these locations are above like breadbasket regions, let's say, where a lot of crops are growing, then they can represent a systemic risk because they could lead to food insecurity issues. And then, of course, we have also cascading effects in time. So if you have heat wave conditions for a long time, that can intensify or lead to drought conditions, which can lead to wildfires, as we experience very often during this summer in different locations all over Europe. Yes, so these are all reasons to understand these extremes. And just like something which might be trivial for some, but maybe not that trivial for others, as we are multidisciplinary crowd here. So when an atmospheric scientist or a climate scientist wants to understand extremes and studies extremes, we usually don't like to rely that much on statistics. We think that the statistics is more abstract, so we do like to look at maps. And we like this tool, the composite maps, very much. So basically, you select, let's say, like at the location marked by the green dot. So if you look there, then we have selected like the 20 most extreme realizations of temperature there, so 20 heat waves, let's say. And then we are averaging the corresponding spatial patterns over all these 20 events to see how, on mean, how weird they are or what are their common properties. So this is what I mean with the composite maps. And usually temperature is also very much governed by what is going on aloft. So the positive temperature values are related to strong high pressure systems usually, and negative temperature values are related to low pressure systems. And now let's, at the end of my theoretical introduction here, let's try to bring things a bit together. So we had these three cases of the shape parameter from extreme value theory, and the negative shape parameter and the zero shape parameter are a bit like, can be similar. So whenever you have those cases that the probabilities of extremes decays exponentially, you can also expect that you might find this, the large deviation laws for averages, because then the exponential law, because then the large values will not dominate your averages. So you might expect that you can estimate a rate function, which doesn't have to be quadratic, but you can estimate something. And then also in these cases, the composite maps you are looking at, they are representative because the events are similar among each other. And the special case is, as I mentioned before, the case of quadratic rate functions, when you can expect that the more extreme the events you select, the better your composite maps become in terms of representing the events over which you are averaging. And then when you have the fat days, in that case, the exponential large deviation laws don't apply. And your composites, of course, are not representative because they are dominated by the largest values. So they don't represent the mean extreme values. Yes, so this is basically an overview of the tools I use. And now let's see what we find in case of the atmospheric circulation in case of extreme events. So let's start with these relatively unsurprising large-scale extremes. And I will start with something I did during my PhD, and is related to Valerios and Tobias' work. So they have shown that in chaotic systems, especially in high-dimensional chaotic system, the GPD shape parameter is negative but close to zero. And this you can find if you connect like the properties of the attractor with the statistics of recurrences in the phase space. And they find that the shape parameter you get then, so it's the inverse, the negative inverse of the dimensionality of the system. And since the system is high dimensional, then that shape parameter will be always negative but close to zero. And we checked this by running long simulations in a quasi-geostrophic atmospheric model, which basically models the mid-latitudinal atmospheric dynamics. And then on the plot there, you can see the shape parameter, the convergence of the shape parameter for energy observables at different latitudes. And what you see is that the convergence is quite slow, but it does go towards this theoretical shape parameter, right? But still, so even though the shape parameter is negative, still we have looked also what could be the absolute maximum value which you can compute, and we found that it's 200 times the mean value actually. So still surprising low probability events cannot be excluded. And especially if you don't have long enough simulations. Now to the large deviation theory applications, so estimations of the rate functions. So we have estimated rate functions of temperature observables in two different models. One is a purely atmospheric model, but a general circulation model. So it's already more complex than the one I was showing to you before. And then the other model was like a full-fledged simultaneous climate model. And so in case of the general circulation model, we can estimate the rate functions at each latitudes because the latitudes have the same statistics, and the, not much varies with longitudes. And in case of the climate model, we estimate the rate functions in different regions because we have orography, right? So they might change. But okay, and then how we estimate the rate function is that first we start with smaller averaging block length. We compute this rate function estimate, and then we increase the averaging block size, and then we see at the end whether the shape of these rate functions is converging. And so what you see for both models is that actually these rate functions converge at averaging block size is approximately 10 to 20 times the integrated autocorrelation, so the typical time scale of the system. And as you see, they are often, they look quadratic. So that's important to remember, quadratic rate functions. And then what you can also do, for example, with these rate functions nicely, you can compare different types of simulations if you want to have a look at the effect of increasing CO2 concentrations, for example. So by the way, when like all the simulations I am mentioning are in a steady state. So these are all basically stationary state simulations. But so what you see here is that in case of if we increase the CO2 concentrations, then we get broader rate functions. And that means that the extremes will become more frequent, but also more persistent with global warming. We also estimated rate functions of purely like atmospheric variables, so not surface temperature, but also jet stream related indices. And also in this case, we often find like that they converge like for averages around 2 months, and that they look quite quadratic, maybe with the exception of the jet speed index, which is more asymmetric, but we find very often quadratic rate functions. Now, let's have a look at the anomaly patterns related to these large deviations or to these large anomalies. And I have selected here like the 20 highest temperature anomalies in the location marked by the green dot. So we took this location because we were interested in the 2010 Russian heat wave. And we had these 1,000 years model simulations, and we selected, as I mentioned, like the most extreme 20 cases, and we are averaging over the atmospheric anomalies related to that, and we get these patterns. And the point is also that, as you see, so even though it doesn't matter if you select actually all extremes or if you select only the ones which are closer to the threshold, because the spatial pattern doesn't really change, which means that there is a typical spatial pattern representing the extremes. And also if we look at individual realizations of extreme events, as you can see 3 examples here, so they are all a bit different from each other, but they definitely share common spatial characteristics. So they are similar among each other and they follow these spatial patterns. And then we were interested at another heat wave, the one I mentioned before already, which hit Northwest America, so the 2021 Western North American heat wave. And we checked actually in different locations over the US whether we find typical patterns. And usually like over the land locations, we do find this typical pattern. So now you see again the mean over all the extremes, but the red dots show you where in case of the individual extremes, where the maximum of the high pressure systems are. And then you see that the red dots are close to the green dots. So the events are to a certain degree similar to each other. And then we can also do things like where we can ask ourselves, okay, so we have these typical patterns in the model events, but does the observed event as it is in the reanalysis, does it resemble these model events, or can it be one of these typical model events? Could it be part of the ensemble of model events? And then we do find that in both both cases of unprecedented extremes, from the perspective of the large scale spatial patterns, these events are typical extreme events. Of course, the global warming can still make these events more frequent, right? But they are part of the natural variability of the climate system. Yes, and then I wanted to have a bit of a closer look at basically the same event, but more at the spatial temporal evolution leading to the heat wave. And you can see here again, like averages over most extreme events, and where you can see the peak 0 is the peak of all these extreme events. And then we can follow back in time, basically their mean spatial temporal evolution. And what we see that also this mean spatial temporal evolution makes sense. First, you see like a wave anomaly. Then you see also already 16 days before, you see some anomalies. And then this wave anomaly undergoes wave breaking. And then at the end, at the peak of the event, you basically have like a blocking system. So this mean makes sense as well. And then I checked how similar are the individual events at each time step going towards the mean. So what we see is that already 17 days before the mean of the events, there is a positive mean spatial correlation among the events and the mean over all the events. And then this spatial correlation is increasing when we go towards the peak, and the variability decreases. And you can see it also for the 2-meter temperature and also for the related circulation anomaly. So as we approach the peak of the event, the similarity is increasing among the events. And these bluish dots are actually the actual event that was observed based on reanalysis. And you see that over all this time period, the actual event is close to could be one of these model events. So it shares these typical characteristics all over the time period, but it fluctuates around the mean spatial temporal evolution. Yeah, so the red curve, no, like it's not very important. The red curve just tells you the similarity between two subsequent days, like how similar is the day for the mean over this day with the next one. So it shows you just like that the daily patterns are similar to each other, the mean patterns. And then this shows the spatial correlation among the events with their mean, with the spatial means, and the variability, like the whisker plot showed the variability. And then this turquoise dot is what you get, how similar ERA 5 is to the mean of the model events. Yeah. Yeah. Yes. To the model evolution. Yeah, so the dot is ERA 5, and you see that the dot is also always around what the model events does. It follows them. It follows the mean, but it fluctuates around it. And also at the peak, the ERA 5 event is very similar, very typical compared to the model events. Yes, and now let's have a look at the extreme value theory perspective. So this is just, again, like an estimation of the GPD shape parameter for this selected most extreme event in the model. And basically, as according to what I was mentioning before, we get something we would expect. We get a shape parameter which is negative, but it is close to 0. And you can see that it's close to 0 because the absolute maximum, the upper endpoint of the distribution is quite far away to what we have observed in these very long model simulations. So we get, again, negative, close to 0 shape parameters. And this plot is meant to show you actually that the more extreme the events we select, the more similar they get. So first, I select like events of 5 years return period. So I have, I think, 320 events or so. And then I'm showing here, again, the correlation, the spatial temporal correlation between the individual events and their mean. And the black line shows you the mean spatial temporal correlation, so the mean similarity. And what you see is that the more extreme your threshold is, the more similar your events become, so that the similarity is increasing. And then now this reddish dot is again the observation. So the observed event is very similar to the mean over all these events. So so I'm looking at actually at the whole spatial temporal evolution from 17 days until a bit above the peak. And I'm computing the spatial temporal correlations, and I'm selecting more and more extreme events. Yes, and then a few other studies which confirm these results. So a study by Robin Noyel, who showed these typical properties in case of heat waves over France. And there is a recent preprint also by Belinda Hotz from ETH, and also Robin was involved, where they show that the vertical profile of temperature extremes is getting less and less variable and more similar when you select more extreme cases of events. Yes, and then this is related to how the jet stream influence the extremes over Europe, like precipitation extremes. And I don't want to go into details, but the aim is that also in this case, the more extreme jet situations you select, the more connected they are with the precipitation extremes over the Mediterranean. Okay, so let's summarize a bit all these properties we found in case related to the large-scale circulation anomalies. So we often observe negative, close to 0 GPD shape parameters. We often observe rate functions which are close to quadratic, very approximately quadratic, and we observe the typicality of extremes, which means that extremes are similar among each other, their mean spatial temporal evolution is representative, and we sometimes also observe that the more extreme the events, the more similar they become. So, okay, but then before finishing, okay, I would like to show you a bit of cases or mention a few cases where so as we see here, the large-scale circulation-related extremes are relatively unsurprising, but then where do we see surprises? Okay, so where do we find surprises? And we find surprises, for example, in case of non-stationarities. So this is again the study I showed you before, and you see that for strong forcing, we have this very nice convergence towards the theoretical shape parameter. For weak forcing, no. And we also see for some thresholds here positive shape parameter, which is basically a sign for surprises, right? And this positive shape parameter is because the system has a regime behavior in this case, and basically when we are selecting the extremes, we are mixing extremes of both regimes. So non-stationarity leads to surprises. And similarly to this, of course, also tipping points or like global warming can lead to surprises. Then in transition zones. So I show you that this in mid-latitudes we do have these typical patterns, but then there are like transition zones where both extratropical and tropical dynamics can lead to extremes, right? And then in those cases are harder to disentangle typical mechanisms. So this is actually a very recent bachelor thesis at the ETH by Jonas Egerter. I co-supervised, and we were interested at this case at a humid heat wave, so which hit Shanghai in 2003. So that's why we are looking at here at wet bulb temperature anomalies. And we found that like one day before the peak of the heat wave, there was a tropical cyclone hit land. And this was a tropical cyclone Imbudo, which is a very extreme tropical cyclone that hit this region. And then Jonas basically found that these tropical cyclones with Lagrangian backtracking algorithm, that these tropical cyclones contributed to the extremeness of this humid heat wave. But then also he looked at other humid heat waves in the region, in the records, and often tropical cyclones don't play a role. So often you just have that high pressure center, which is a bit shifted, and that can already cause humid heat waves. So you can have humid heat waves are over Shanghai, can be related to tropical cyclones, but they don't have to. Still, the co-occurrence is quite frequent. Okay, but then this gives you, if you have several mechanisms lead to extremes, this might give you surprises as well. And now coming back to the Western North American heat wave, I'm plotting now also the observed anomaly value. So this is over a small region, so we can consider it as a local value. And as you see, this observed anomaly value, so if we look at small scales, is at the far edge of the distribution we could sample in those long, more than 1,000 years of model simulations. So it looks like an outlier from the statistical perspective, but then also it is actually very close to the absolute maximum you can get. So it's hard to say, was it a typical event from this local perspective or wasn't, because even if it was a typical value, it would have a very long return period. And then also other studies have shown that when you look at local temperatures during these exceptional heat waves, different processes lead to the exceptional values in different locations. So in some locations, adiabatic warming was more important. In other locations, diabatic warming or downslope warming, which is then related to orographic effect, and the lack of soil moisture as well. So on small scales, you can get surprises. And also on small scales, there is more heterogeneity, of course, there is more randomness, and we often observe also positive shape parameters, like for example, for rainfall distribution. Yeah. So yeah, surprises can happen on small scales. And then surprises can happen in terms of societal impacts. So in case of societal impacts, we have like a nonlinear relationship between the risk and the extreme event, which is then called hazard. In a recent study done by Mariam Kruma in our group, she found that, so she looked at what leads to child malnutrition in Western African children, and she found that several factors are important, and some of them are related to the climate, like drought and heat waves, but others are, of course, related to vulnerability and conflicts and socioeconomic indicators. But also, like this complexity and this nonlinearity leads to surprises in terms of impacts. And finally, I would like to summarize the whole talk. So as I was showing you, atmospheric extremes related to large-scale circulation anomalies are relatively unsurprising. which is good because that makes also our weather dynamics, our climate dynamics stable, if we forget about global warming. So we then often find negative, close to zero, GPD shape parameters, quadratic rate functions, and we find the typicality of extremes. And surprises can be found in case of non-stationarity, of course, like regime behavior, tipping points, global warming, in case of transition zones between tropical, extratropical interactions, small-scale processes, and societal impacts. Yes, thank you very much for your attention.
Thanks a lot for the presentation. And yes, please, the floor is open for comments or questions. Fredrik.
Oh, thank you. This is very interesting. So about the first part, we have written two papers, one with George Milosevich, Philippine Ruby Poza, and another with Valeria Mascolo and Alessandro Lobo. So in this paper, we try to explain the phenomenology you describe for that there is this similarity between the spatial temporal pattern or heat waves. So to explain why the patterns don't change when we go more and more through the mass. So I think everything, what we try to explain is that it is because it is close to Gaussian. And so I think this is very, all this is very consistent with what you write here, the fact that there is close to zero for the shape parameter and near quadratic rate function estimate. Also the typicality of the extreme. So I think what is much more difficult is to understand this departure from Gaussianity. Of course, it cannot be exactly Gaussian.
Yeah.
So the question is how to depart from Gaussianity. And so can we see this either in patterns or probabilities? So we were not able to answer this question because of the lack of data. I don't know if you have a clue about this yourself.
Yeah, so I think that this Gaussian behavior is like really a characteristic of two-dimensional turbulence at mid-latitudes, where these patterns dominate the extremes and persistent patterns lead to persistent extremes. And so I would expect that in these latitudinal regions, this typicality makes a lot of sense, and then it's hard to see deviations from Gaussianity. Of course, you might have like still in case of individual events like this, I haven't checked, for example, like maybe it would make sense to look at the most atypical event or the event which is has the largest departure from this mean temporal evolution, and look what the event does differently to understand what could lead to the more like non-Gaussian kind of behavior. But from a statistical perspective, we do expect this. We do see this Gaussianity. But then in some regions where, as I mentioned, like where it can be like different processes leading to an extreme event, like these transitional regions, or it can happen, of course, that not everywhere, just like there is one dominant way to produce the extremes. So in some regions, then you might see more deviations, I guess. And it is a matter of the variable as well. But I think everything which is driven from the large-scale circulation at mid-latitudes tends to show this behavior. I haven't looked at tropical dynamics yet, so maybe in the tropics you get something else.
Please. Yes.
Can I ask a very naive question?
Sure.
Perhaps it's not surprising that you get surprised when your system's non-stationary.
Yeah.
Because you're seeing an evolving system.
Yeah.
Is there any theory behind how this evolving system, global warming is very different from a tipping point. So
yeah.
How you expect the distributions to change under the different types of non-stationary behavior we talked about?
Yeah, so I can just come up maybe with a few like storylines or like some kind of hypotheses. So in case of like the global warming effect on the large-scale atmospheric circulation, the effect seems to be rather slow and seems to be quite smooth. And actually, it's still debated how the large-scale circulation is changing with global warming because the jet stream and the Rossby waves do their own thing in a way. So in that case, I think we will still have also with global warming, we would still have some typical patterns and typical anomalies because the basic properties of the system will not drastically change, but we will probably see at some point some shift in these patterns. Or maybe we might see among the individual events more variability. So maybe the mean is then less representative or the other way around. So I think in case of global warming, it would take some time to see these changes, and it wouldn't be super radical changes from the perspective of the atmospheric circulation. Of course, the changes might be radical on the ground, like when it's about the local small-scale effects and impacts.
Right?
Yeah, this result that surprises can appear on the small scales. Is this a general statement that you can also derive from a large deviation principle? For example, if you take blocks in space or something, or does it depend more on the heterogeneity of the space?
Yeah, I haven't derived it, and it was actually like an idea I got during the EGU talk, during the award talk of the nonlinear processes, where like the speaker was also pointing out that like on small scales, randomness is more important. On large scales, you have the rules, you have the Coriolis effect, you have the wave. So there is something which is governing the whole circulation and organizing the circulation. On small scales, you don't have that. But then, of course, like also there are non-exponential large deviation laws, so maybe those might apply to the small scales. But it's hard also to test this with the models, for example, because the models are known to not be good on small scales, and you need a lot of data. So not sure how to test it, but there is still a lot of unclear pieces of the puzzle.
Yeah, so I have a follow-up question about large deviations. So I'm just curious, I'm on more theoretical side.
Yeah.
So you see, so large deviations, mathematical theory, so which describes events which occur with exponentially small probabilities, yes? So we have some limits and so on. So is it really applicable to real data? So because exponential small probability is actually, so practically never, so
Yes.
zero. So does it really work?
Yes, of course. Of course, the applications are, it doesn't always work. So the climate system is a huge system, and it's very heterogeneous, and different properties, like the ocean is much smaller, much slower than the atmosphere, right? So, and you might have this regime behavior and long-term memory, and there is everything in this system. But it turns out that for the atmospheric circulation-related anomalies, it works very well because very often probabilities decay exponentially. So then we can use this tool for that part of the climate system. But then, of course, if you would an open question is also like in case of the ocean, for example, like some other types of large deviation laws, maybe like not the one which is linear with n, but some exponent on the n that might work. And of course, it doesn't work perfectly, right? So it's more approximations, but it's still surprising how well it works for the atmosphere and especially for the large-scale structure-related extremes.
Maybe just sorry, another question. So what is the small parameter or the large parameter?
Now, in my case, is the averaging block length.
The length of what?
The event.
Time.
Averaging window.
Okay, so but I mean time, so if you're on the time scale, say 100 years, yes?
No.
Or smaller.
No, but like we find convergence like for averages of, let's say, 1 or 2 months. So it's basically, these are long periods, of course not one heat wave lasting that long, but there are maybe several heat waves in that time period. But then, of course, then these typical patterns are somehow related to this, but we do find a similarity and typicality, which can be explained by large deviation theory as well, also on smaller time scales. So that is more like dynamical systems, path-related large deviations. Could be explained by that.
Small, so small in comparison to, related to what? To what scale? So small in relation to.
What do you mean small?
I mean, you say month. Month is small in relation to. So a year or 10 years or 100 years. So what is the?
I mean, I think you.
Okay, so
in relationship to the characteristic time scale of perturbation. So a month is long, okay, but it's sub-seasonal, so it's still within one season. So it's a bit of a sweet spot.
Yeah, basically, it doesn't make much sense to go over the length of the season, because then you are mixing winter and summer.
There's more parameters one over time.
Yes. Jeroen and Nico and Ulrike.
Okay, thanks for your talk. I really want to state my bias and also I'm not really in this field. But one thing that so I work in dynamical system. One thing surprises me is that there is a statistical point of view you take. Like there's some kind of assumption that fluctuations or some kind of statistic tells you something. And if you look from the dynamical system point of view, that's not obvious at all. It's usually, as Ilya says, there's some specific situations and specific limits that these things work. And so one thing that actually concerns me, maybe a bit more philosophical, is that you said in the beginning something about when do we get surprised. I think we get surprised when something is outside the expectation. But this expectation comes from the simple models that we have. So we shape our expectation based on some kind of like way of looking at it. And for instance, you say large deviations, exponential decays, and so on. And if it's not like that, you say, oh, this is strange. But if we would enlarge the set of models we have, we understand better what typical models actually do. You could much better understand. I mean, my point is a bit that I think that what we tap into is very narrow, like large deviations, right? Quite narrow. It's difficult to prove in any kind of examples. You can give counterexamples, almost anything. So it's so to hold back on this small set of theories and say, okay, when we look at it, we see all these theoretical phenomena, I'm always a bit suspicious, because if you just take some less naive models or something like that, you see lots of crazy stuff going on, things that don't hold to this kind of like behavior. So if you look in reality, I would say,
what kind of models do you mean?
Well, there's all kind of other models you can have. The large deviation is not some kind of like given fact. It's
Do you mean other tools or?
Yeah, there's so large part of the mathematics we have is given by what you could do with calculus, say 50 years ago or something like that. And so there's a lot of by hand calculations like statistics that we can basically solve. But when we look at real systems, which are very nonlinear and very stuff like that, then it seems to be very far away from these idealized models in some sense. Yeah, so I'm a bit surprised or concerned or whatever. How can you fit these other idealized models that we know if you look at it in dynamical systems, very rarely apply in some sense or under very strict conditions. Why would
but these are large Earth system models you're using, isn't it?
I'm using a set of Earth system models actually.
Yeah, so they're not naive.
So they are. I am.
Absolutely not naive.
My models are naive.
Yeah, but
No,
they're not naive.
because there's a large scale of phenomena, not just the ones that we are familiar with. You can see all kinds of craziness happening. Yeah, very easily. So why would so my question is like, why would certain type of simple models relate to these things, and where are all the other phenomena that could also happen that are not studied in some sense? And so are we missing the question?
I'm interested at extremes, right? So I'm looking at extreme events, and then there are a few mathematical tools I can use. Basically, extreme value theory, large deviation theory. I mean, these are the main tools from the statistics. I cannot use everything, right? So, okay, I'm using these two tools, extreme value theory, large deviation theory, and also how, like more the atmospheric perspective, how the events look like, and also making like rather easy calculations, how similar they are among each other. And I think it's interesting how these things still fit. And of course, also the atmosphere is not random variable and it's not independently identically distributed, but the correlation decay is rather fast. And then so it means if I average over a block which is longer than 5 days, let's say, then those averages are not much related anymore to each other. So it applies quite well, quite surprisingly well, and I think it's of course it's a big puzzle and it's not solving everything, but it's interesting for me to point out these similarities between what you get from a statistical perspective and what you get from an atmospheric perspective and how it looks like.
But you also, of course, indicated these dynamics, or that certain states will lead to, say, extremes, which is more an idea that where you are in state space somehow will say
Can I
something.
just say 2 words? So, I mean, the starting point is a set of papers of Van den Eyden, Galfi, and others who studied the occurrence of rogue waves. Okay, so they were studying, instead of trying to find a way to get to the rogue waves, they studied that assuming a rogue wave exists, what are the most likely initial conditions that lead to the rogue, and they lead after a certain time to this rogue wave. And they found that this problem obeys a large deviation property. Okay, so basically there is a typical path in phase space that leads you, and atypical initial conditions that lead you to this event. So this is one thing that is associated to the typicality Melinda was describing. So that's one level of large deviation in path, and I think she showed also the evolution in time that follows. That's, I think, a very original part she showed. Shows that a long time you get a coherent path in space, even in very high dimension. That's one side. The other side is locally, statically, if you collect statistics. So that is a large deviation initial condition. So there is no actually small or large parameter, except the size of the event you're trying to target. Another thing is if you look statically and do climatology of persistent events, then you fall quite clearly into the large deviation domain of attraction in this case. So that's what one finds. If you have some sort of a regular stationary regime, if you have transition between regimes, you're mixing apples and oranges and things that don't work. And I mean, Freddie showed also how to find the deviation from Gaussianity using great event algorithm. So you find that you can, push a bit harder. So this is, so she did, I think the work she did is collecting the statistics and showing that you have a good convergence of rate functions and the events surprisingly look similar to each other. All these events, so let's say each event is very different, but the more you target extreme events, the more they are similar to each other. So, and this is a bit of surprising with respect to the usual commonsensical view of extreme events as something out of scale, something that does not obey any rule, basically. But they do look similar.
From a dynamics point of view, it's not so strange because if you basically follow some kind of like.
I agree. That's why. So the idea is that you find this even in incredibly high dimension. So that is the very high dimension. So there is a special atypical path. When you enter this path, you go up a valley, you're gonna end up to the peak. So that's basically in a nutshell. Sorry for taking time.
No, thanks.
But it declared my bias.
Yeah, of course, we have to.
Can discuss later.
I think last question by Nico.
Yes, no, super good. Thank you so much for the talk. I was wondering whether you can condition on multiple things at the same time. So especially if you have multiple processes, maybe, and you're mixing stuff and mixing paths, if you condition on multiple conditions, maybe you get again the typicality of that specific rare events. I understand that maybe you have even less data.
Yeah, so you're meaning more like this compound extreme perspective where you have like extremes in different variables and you're conditioning somehow on both.
Yes. If I understand correctly, you're conditioning on having one observable bigger than something, that threshold, right?
Yeah.
If you have multiple observables, that might allow you to, select a specific type of process happening. Maybe that.
Yeah. It's not that trivial to do it if you have multiple observables. It's just simply selecting the extremes becomes more challenging.
Yeah.
But it doesn't exclude, of course, the idea of typicality. And also what we see, like with the jet stream study, I showed it only shortly, is that when we go to more extreme levels on both sides, the variables are more and more connected with each other, which is then also in line with the typicality idea.
Okay, yeah, we stop here. Thanks a lot.
Thank you.